Okay, we were saying that since the electrons are moving, one of the chlorines are going to have more electrons. So I'm going to have what we call a dipole, yes, in this direction now. So this is going to be a density positive, and this is going to be a density negative. Remember, this is not permanent. The permanents are the dipole-dipole. These are temporary dipoles. That temporary dipole is going to have an effect on the molecules that are next to it, and it's going to produce what we call another dipole. Why? Because this positive zone is not a charge, but this positive zone is going to attract the electrons of another chlorine that is attached to another chlorine that is next to it. Do you understand? And in this case, this temporary dipole is going to produce what we call the it's going to produce what we call an induced dipole. Yes? Now, these are the weakest one of all these intermolecular forces, and we call them van der Waals forces, or also they call them London dispersion forces. Okay, those are the names that we give to this temporary dipole induced dipole thing. Now, that doesn't happen only in the multi-atom molecules. It happens also in cases of the noble gases, the big noble gases that, like xenon, for example. Xenon has so many electrons around it that eventually the electrons, and I think argon does it too, and xenon is going to produce a temporary dipole that again is going to produce an induced dipole in another xenon molecule or atom, and they are going to form what we call a London dispersion forces or van der Waals forces. That is the only explanation that we have that we can liquidify a gas that is nonpolar. That is, yes, nonpolar. Okay? So far so good? We are done with intermolecular forces, guys. Now, the only thing that I need to clarify, because that sometimes it's very, very confusing for you. If I need to melt something, if it's a discrete molecule, what is the force that I need to overcome? Intermolecular forces. Yes? So we need to overcome intermolecular forces. If I need to melt a metal, what are the forces that I need to overcome? Do we have covalent bondings there? Do we have ionic bondings there? We have metallic bonding, yes? So that is the force that we need to overcome, metallic bond. Do you see the difference? The metallic bond is much stronger than any of these intermolecular forces. That's why the metals melt and boil at a very super high temperature, but not so high as many of the ionic compounds, yes? Because in the ionic compounds, which are the forces that I need to overcome? Ionic bonds. And for breaking down an ionic bond, you need to know that in the bonds, we need to overcome the forces of attraction. Which kind of forces are there? Electrostatic forces between these ions, okay? So they are super high forces, and besides that, each ion is surrounding, depending on the structure, But that can be one of the questions. How many atoms you have surrounding, let's say, the atom of sodium in sodium chloride? You have 1, 2, 3, and 4, yes, on the sides, in each side 90 degrees, and 5 and 6. So these are going to be in a plane, and these are up and down. Because the sodium chloride, I don't know if you remember the structure, you should, it's 1, 1, 1, 1, and it's like a cube, yes? So in that cube, I'm going to have a chlorine here, chlorine here, chlorine here, chlorine at the bottom, chlorine at the top, and behind, yes? So in the ionic compounds, we need to overcome what? The ionic bond. And the last one is the giant covalent. Yes? In the giant covalent bonds, what do we need to overcome? Let's say that we want to melt graphite, or we want to melt sand, which is silicon dioxide. What are the structures or the bonds that we need to overcome? Look at this. It says covalent, yes? But do we have only one covalent bond, like in the hydrogen chloride? We have bonds all over the place. We have bonds in all directions. That's why they have so high melting and boiling points. Actually, those are the stronger bonds. That's why we have such an amount of temperature to be able to melt graphite, for example. Because the covalent bond, that is the one that we need to break when we need to melt a giant covalent compound, is the strongest of all bonds. Yes? So which are the stronger ones? The covalent bond. Then what? The ionic bonds. Then what? The metallic bonds. That's why this one has higher melting and boiling points than the ionic bonds. The ionic more than the metallic, some of metals, depending on the metal, and I'm talking in general, okay? And the metallic bonds bigger than any of the intermolecular forces. Which is the stronger of the intermolecular forces? The stronger one are hydrogen bond. And then dipole-dipole. And then van der Waals. Okay? So from bottom to top, you have which has the strongest bonds. And in the intermolecular forces, I also put it from bottom to top, which are the strongest and weakest here. So if I need to melt a compound that has only van der Waals forces, first of all, most of the time they are going to be gases. In the second one, dipole-dipole. In the dipole-dipole, and I say here that they are most of the time gases, because we have some liquids here. Oil, for example, is a non-polar covalent compound, but the size of the molecule is so big that we need to, give me 1 second. I was saying that the van der Waals forces are in things like, for example, coconut oil. Coconut oil is a non-polar compound, but it's a solid. But why is that? The molecules are so big that they are going to be tangled to each other. And besides that, the longer they are, the more surface of interaction they are going to